Hello everyone, and welcome to the Waves and Oscillations portion of the course. Now, despite the name, we're actually going to start with the oscillations section, and we're going to move on to waves in future weeks. Oscillations are useful to understand in their own right. If you want to understand how the suspension in your car works, or a pendulum, or there's plenty of other examples of oscillations on their own, but they're also important for understanding how waves work. Waves are essentially just a whole stack of oscillations lined up next to each other. Now, there's a whole variety of kinds of oscillations. An oscillation in general is just any kind of back and forth motion that repeats itself in the same or a similar manner over and over again. But for our purposes, and with an eye to the waves we're going to cover in the future, we're going to cover a particular kind of oscillation this week called simple harmonic motion. Now, thankfully, it's simple, as the name implies. It's pretty much the simplest kind of oscillation you can get. There's a variety of reasons we want to cover simple harmonic motion. First, it's fairly easy. Second, it's actually really generalizable. Even further complicated kinds of oscillations can generally be described as combinations of these simple harmonic oscillations in some sort of a way. And third, when we do start talking about waves, there's all kinds of waves and other phenomena that can be described by this. We're going to start off today by talking about a mass on a spring, and in the future we're going to apply that to a swinging pendulum and various other things. But this simple harmonic motion shows up in the motion of particles in a solid or a gas. It could describe pressure waves like sound waves. We're going to use it when we get to light. When we talk about waves, we're going to talk about light waves being described by this kind of oscillatory behavior, and even other phenomena like oscillating circuits, like alternating current circuits, can be described with this kind of simple harmonic motion. So, however, like I said, we're going to start with a really simple scenario which should already be reasonably familiar to you. It's a mass on a spring. So you should already have a pretty good understanding of how a mass on a spring works. You should be familiar with Hooke's law. Hooke's law states that the force experienced by a mass attached to a spring is going to be equal to negative kx, okay? Where x is the displacement from equilibrium. So let's just mark here the equilibrium position of our block. If I stretch my spring so that it goes towards the right, like so, I would now expect there to be a force on the mass which is pushing it to the left. Okay, we call this a restoring force. It's always directed to push our object back towards its equilibrium position. Similarly, if I push it all the way to the left, it's going to be a force to the right. The further away from equilibrium I push it, the bigger this force is going to get. But as long as I'm on one side of that equilibrium position, it's always directed in the same way. Now, because you can see if I'm on the left, as I am now, it's always going to be accelerating towards the right. So no matter what my starting scenario is, I could be moving away, I could be moving towards, I could be at rest. I'm going to accelerate towards the right until eventually I'm going to have enough speed. I'm going to pass at equilibrium position with some speed, and only then will I start slowing down and accelerating back towards the left. And eventually, the same thing will happen. I'll move towards the left, I'll cross that equilibrium point, and we can see how we're building up an oscillation here. Now, it'd be nice if we could describe this oscillatory motion in some kind of a way without having to draw dozens of pictures of the position of the mass and the force. Hopefully you see where I'm going here. The simplest thing we can do here is draw a plot of the displacement from equilibrium of our object against time. Now I'm going to define rightwards as being positive, leftwards as being negative, and of course the equilibrium position is going to be 0. And we should end up with something that looks like this. So you can see here we're starting with a positive displacement, which indicates that we've got our mass starts towards the right, and we accelerate towards the left. So you can see our position is moving towards the left as well. Our velocity is towards the left and our acceleration. And we speed up, we hit the equilibrium point, then we slow down, we come to a stop, we turn around, we move back towards the right, we cross over the equilibrium point, and we come to a brief rest here at our starting position, and then we continue on. And so this graph here seems to describe quite well what we're seeing in what we'd expect from our mass on a spring. Now, so far, nothing I've said here applies specifically to simple harmonic motion. This describes pretty much any kind of oscillation, and we want to have a bit of vocabulary to also describe any oscillations we come across. So the first thing I'd like to cover is the amplitude of our oscillation. So the amplitude is just how big our oscillation is, how far from equilibrium do we move. And we can see we move as high as this, our starting position, and as low as our ending position. So we could mark here, this is our amplitude here, this is negative amplitude here. The amplitude is given the symbol A. A stands for amplitude, that should make a lot of sense. In this particular case, the unit for amplitude is the meter, the SI unit, because we're talking about a physical displacement. In the case of an oscillating current, then your amplitude would be in amps, or an oscillating voltage would be volts. You could imagine light, electric field would be your amplitude. For sound, it might be pressure. So the amplitude is just determined by what it is that's oscillating. Not so for the second thing I want to talk about, which is the period. The period is what makes our oscillation an oscillation. It tells us how long it takes before our oscillation repeats itself. So you can see if we start here, at this position here, we'd say, well, how long before our oscillation repeats itself? Well, it gets back to its starting position here. So this time here is 1 period. Similarly, we could say the same between any other 2 points. Here's the first trough. How long before it gets back to negative A again? This is also your period. I would recommend just a slight bit of caution. If I were to start here, for example, and I want to say, well, when do I next get back to where I was? Well, that's here. But of course, in that case, I'm going the opposite direction than I was here. Really, what I'm talking about is when am I back in the same state as I was before? And in that case, it's the same state is all the way over here, so this corresponds to 1 period. Obviously, if we're talking about a time, yes, our unit of time is the second, so the units for period is also the second. Sometimes, however, actually for a lot of oscillations, we're less interested in how long it takes before we repeat ourselves, because generally a lot of oscillations repeat themselves over a very short period of time. We might be more interested in asking how many times does this oscillation happen per second or per some particular amount of time. And so to describe that, we have this concept of frequency. So frequency is just one on time. It tells us how many oscillations per second, or how many times we repeat ourselves per some particular time. If we've measured our period in seconds, then obviously our unit is going to be inverse seconds or reciprocal seconds, or technically it's oscillations per second, but all of those are kind of wordy, so there's another unit we use, which is the hertz. Symbol Hz. It's named after some guy who did a lot of work with oscillations. Okay, so you might have noticed that our simple harmonic motion, our oscillation of our mass on a spring, I've drawn here, is looking quite sinusoidal, and that's not a coincidence. So I'm going to just assert here, I'll come back and I'll prove it in a minute. I'm just going to assert that the formula, the equation for this oscillation, mass on a spring, is given by x equals a cos omega t. So x here just represents the displacement, a is our amplitude as expected, t is the time axis over which our oscillation is occurring. Before we know anything else, we can see that this kind of makes sense. Cos of anything is always going to be between -1 and 1. So A cos something is always guaranteed to be between negative A and A. As t increases, the argument of our cos function is going to increase, and so we'd expect some sort of oscillatory behavior, which is what we're getting here. But what on earth is this omega? Now, you would have seen omega in rotational motion. You might know that it's the angular frequency. But what does that mean? We haven't got any angles here. Our mass is just moving back and forth. How does this make sense? Well, the angle we're talking about here is really just the argument of our cos function, okay? So we've got some angle in here, and we want to be able to say cos of some angle. We need to turn our time into an angle so we can take the cos of it. Obviously, it has to be related to the period or the frequency in some way, because it's obviously going to be the thing that determines how quickly our cos function oscillates up and down as time progresses at some particular rate. We can work out how it's related just by considering if we're starting, as we are in this example, we're starting at our position here. After some time, so here's this time here is going to be t. So I'll mark that one period. After one period, we're back to where we started. What has to happen to the angle, this argument, in our cos function to get back to where we are? Well, cos equals 1 when t equals 0. The next time cos is going to equal 1 is when the argument equals 2 pi. If you imagine your unit circle, you've traveled all the way around the unit circle once. That's 2 pi radians, or 360 degrees, but we're going to stick with radians for this course. Simplifies a lot of things. So let's write 2 pi, our angle, equals omega t, but the t in this case is our period, so capital T. We can rearrange that, and we'll see that omega equals 2 pi on t. 1 on t is f, our frequency, so that's just omega equals 2 pi f. So you can see our omega, angular frequency, is just frequency times an angle, times 2 pi. So hopefully that makes some amount of sense. We'll come back and we'll talk about this angle, this argument of our cos function in a later video, but hopefully that at least gives you some sort of justification for why there's an angle popping up and how it relates to the frequency or the period, which make a lot more physical sense. Okay, so we can see that this function, it's quite reasonable. It describes the behavior of our mass on a spring, but we'd like something a bit more solid than that. So let's consider what other implications there are with this equation. Get rid of all this. So I might also be interested in what's the velocity of my particle, of my mass on a spring, as it's oscillating back and forth. And we can find that fairly easily. We know that velocity, we want to find velocity, equals dx on dt. Okay. Now, x is a cos omega t. The a is a constant, it doesn't change, so it's just going to come out the front. So we have a d dt of cos omega t. Okay. What's the derivative of cos? Negative sign. Our coefficient on our t pops out the front, because we're taking a derivative with respect to t, but this coefficient just pops out the front, and we end up with negative a omega sine omega t. Okay? So this is telling us our maximum velocity is a omega, our minimum velocity is negative a omega. It's a sine function, so it's going to look something like this. And I've stuffed that up a little bit, There we go. So you can see whenever our position is at a minimum, when our position is 0, our speed is going to be a maximum or a minimum, depending on which way we're going. And whenever we're at our furthest extent from our equilibrium, then briefly, our velocity is going to be 0. So again, this matches what we understand. It's still not hugely conclusive, and I promised you I'm going to prove before the end of today that our simple harmonic motion, our a cos omega t, describes the mass on the spring, or the mass on the spring gives a simple harmonic motion. So let's take it a step further. Let's ask, what does the acceleration look like? So the acceleration equals dv dt. Okay? So that's, again, the omega is a constant, a is a constant, so this is negative a omega d dt of sine omega t. What's the derivative of sine? Cos. No extra negative pops out, but we do pop out our coefficient again, and we're going to end up with, and I'm going to write this a little bit differently here, negative omega squared a cos omega t. Okay? Now, this is quite useful. It tells us the acceleration is at a minimum when the position is at a minimum. Sorry. It's going to look something like this. I should have changed the color. You can see wherever, it's just the opposite of whatever our position is. I should label this is V and this is A. Now, you might notice something else. This A cos omega t here, it's quite interesting. It's the same as this A cos omega t here. So we just say A equals negative omega squared x. What sort of force would provide this kind of motion? Well, our force equals ma equals negative omega squared x times m. Let's write that as negative m omega squared x. Okay? What's the force on a spring? Well, Hooke's law says the force of a spring, F equals negative kx. Well, here's our k. Let's equate these two. You can see, because this is a constant, our oscillatory motion is given by exactly the same force as the same kind of force, a restoring force, which is proportional to our position. Exactly the same kind of force as our Hooke's law. So as long as we can cancel off the x's, we cancel off the negatives, and we end up m omega squared equals k. Or, might be more interesting if we get ourselves a little bit more room. Let's rewrite this. M omega squared equals k. We can use this to say that, well, rearrange omega squared equals k on m. For a particular spring and a particular mass, our angular frequency of our oscillatory motion is going to be the square root of k on m. So there you have it. A mass on a spring will undergo a kind of oscillatory motion, which is described by simple harmonic motion. The angular frequency of that oscillatory motion is given by omega equals the square root of the spring constant divided by the mass of the oscillating mass. Okay, cool. So hopefully you found that informative. There is something that I've left out here, which you might have noticed. I did assume that our object started at rest. I've just pulled it to the right and then let it go from rest. In the next video, I'd like to cover in a bit more detail how we can approach that in a slightly more clever way, and also hopefully clear up any lingering problems you have about this whole angular component of our oscillatory motion, of our oscillation, despite there obviously being no actual angle involved. Alright, so come back and listen to that.